Testing, testing, 1, 2, 3. Okay, I think I'm not gonna jinx it, but I think we're okay right now. You can see me, and also to update the chat because I forgot to do that. All right, let's start. Yeah. All right. Good time of day, whether it is morning, evening, afternoon, or any other time. I think currently the face tracking is doing a good job, I hope. But if there are any errors, do not hesitate to let me know. Yep, there it is. Okay. Trying to monitor. I don't know whether oh wow, I think the issue is with my internet, not with the face tracking this time. Okay. Do let me know how horrible the streaming is, if it's too horrible. Oh my god, these ghosts are adorably cute. I actually put them there so that I can monitor how bad the Okay. Yeah, I fixed something, I messed something up. This is life. I'm gonna start because I do not want to delay this lesson any longer. And apologies for the issues. I think the trying to fix the internet messed with some things, so sorry about that. Yeah, so I think you can see my screen, which means we can recap. Let's start with a recap. As you know, we are taking this course called Introduction to Machine Learning for Coders. It's a course by fast.ai, which they have like a lot of courses, different types, mostly machine learning, deep learning related. It is taught by Jeremy Howard, one of the top ML, I'd say, researchers and also Kaggle competitors. This course has 12 lessons. We are in lesson number 7, and up until now we've been focusing on random forest. I think in today's lesson there's one part where we are finishing the final part of random forest. I forget which it is exactly, and then we're probably starting gradient descent. So I have this here. I'm gonna review, and yeah. Okay, that's taking its sweet time. Apologies for that. Issues upon issues. Life is like that, you know.
Tree.predict. So we're going to have to write that.
Oh yeah, so we were writing our own RF random forest method by, on our own, with our own hands. So that's what we're doing. There was one last part. We did find better split. I remember that, you see here. But then we even did the forest, I think. I forgot what was the last part we were supposed to do.
Okay. To make this more interesting, let's start bringing up the number of columns.
Oh, okay. Make more columns, give it more columns.
We use. Let's create our tree ensemble again. And this time let's go to a maximum depth of 3. Okay, so now our tree is getting more interesting. And let's now define, how do we create a set of predictions for a tree? And so a set of predictions for a tree is simply the prediction for a row for every row. That's it, right? That's our predictions. So the predictions for a tree are every row's predictions in an array.
One row. Xi? Or... I mean, yeah. We're looking at all the predictions. And what are we doing with it? Summing it up, or... what are we doing?
Okay, so again, we're like skipping thinking. Thinking's hard, so let's just like keep pushing it back. This is kind of handy, right? notice that you can do for blah in array with a NumPy array, regardless of the rank of the array, regardless of the number of axes in the array.
Like a for each?
And what it does is it will loop through the leading axis, right? And these concepts are going to be very, very important as we get into more and more neural networks, because we're going to be all doing tensor computations all the time. So the leading axis of a vector is the vector itself. The leading axis of a matrix are the rows. The leading axis of a three-dimensional tensor are the matrices that represent the slices, and so forth, right? So in this case, because X is a matrix, this is going to loop through the rows. And if you write your kind of tensor code this way, then it'll kind of tend to generalize nicely to higher dimensions. Like, it doesn't really matter how many dimensions are in X. This is going to loop through each of the leading axis, right? Okay, so we can now call that decision tree.predict. Right, so all I need to do is write predict.
So we're returning an array. We're not doing anything with it. Okay.
Row, right? And I've delayed thinking so much, which is great, that the actual point where I actually have to do the work, it's now basically trivial. So if we're at a leaf node, then the prediction is just equal to whatever that value was, which we calculated right back in the original tree.
Wasn't values of predictions okay, so self-val is like the final val, because I know leaf nodes had infinite, they weren't set. Am I wrong?
Constructor, it's just the average of the y's, right?
Average of the y's, okay.
If it's not a leaf node, then we have to figure out whether to go down the left-hand path or the right-hand path to get the prediction, right? So if this variable in this row is less than or equal to the amount we decided to split on, then we go down the left path. Otherwise, we go down the right path.
Okay. And then we're calling, it's recursive again, because it has to be, because we're traversing through, you can even call it a graph, but it's a tree. I'm getting flashbacks. I don't want to discuss it.
Okay, and then having figured out what path we want, which tree we want, then we can just call predict row on that, right? And again, we've accidentally, again, I don't want to think about how that works control flow wise or whatever, but I don't need to, because like it just does, like I just told it what I wanted, so I'll trust it to work, right? If it's a leaf, return the value, otherwise return the prediction for the left-hand side or the right-hand side as appropriate. Okay. Notice this here. This if has nothing to do with this if. Right, this if is...
What do you mean? Because this if... What do you mean?
A control flow statement that tells Python to go down that path or that path to do some calculation.
Okay. I know we have like if sentences that are like in line, which then return values, but this is a control flow. This is a, what do you call this?
This if is an operator that returns a value.
Ooh.
So those of you that have done C or C++ will recognize it as being identical to that. It's called the ternary operator, right? If you haven't, that's fine. Basically, what we're doing is we're going to get a value where we're going to say it's this value if this thing is true, and that value...
Isn't there another way to write this where you don't even need to write the if? You just do a question mark and then colon Basically, oh my god, he's actually showing it in the next line. Okay.
Otherwise. And so you could write it this way,
Or
right? But that would require writing 4 lines of code to do one thing. And also require you to have code that if you read it to yourself or to somebody else is not at all naturally the way you would express it, right? I want to say the tree I'm going to go down is the left-hand side if the variable's less than the split, or the right-hand side otherwise, right? So I want to write my code the way I would think about or the way I would say my code. Okay, so this kind of ternary operator can be quite helpful for that. All right. So now that I've got a prediction for a row, I can dump that into my class. And now I can calculate predictions. And I can now plot my actuals against my predictions.
actuals.
When you do a scatter plot, you'll often have a lot of dots sitting on top of each other. So a good trick is to use alpha. Alpha means how transparent the things, not just in Matplotlib, but like in every graphics package in the world, pretty much. And so if you set alpha to less...
Even in, not just graphic packs, in, like, when you learn about, you know, images in computers, there's RGB, red, green, blue, and alpha, which is the transparency rate. Yep, I remember learning about that.
...than 1, then this is saying you would need 20 dots on top of each other for it to be fully blue. And so this is a good way to kind of see how much things are sitting on top of each other. So it's a good trick for scatter plots. There's my R squared, not bad. And so let's now go ahead and do a random forest with no max amount of splitting. And our tree ensemble had no max amount of splitting. We can compare our R squared to their R squared. And so they're not the same, but actually ours is a little better. So,
Okay, we're comparing the random forest from, where is it from?
I don't know what we did differently, but we'll take it. Okay, so we have now something
I don't know why it works, but we'll take it, basically.
which for a forest with a single tree in is giving as good accuracy on a validation set using an actual real-world data set, you know, bulldogs for bulldozers, compared to scikit-learn.
Oh,
So let's go ahead and round this out. So what I would want to do now is to create a package that has this code in. And I created it by like creating a method here, a method here, a method here, and patching them together. So what I did now is I went back through my notebook and collected up all the cells that implemented methods and pasted them all together, right? And I've just pasted them down here. So here...
Instead of assigning it at a later stage, you just created them all together, right?
This is my original tree ensemble, and here is all the cells in the decision tree. I just dumped them all into one place without any change.
Hello, good morning. Welcome. We're just continuing the lesson we did the other day. Also, we have ghosts today learning with us.
So that was it. That was the code we wrote together. So now I can go ahead and I can create a tree ensemble. I can calculate my predictions. I can do my scatter plot. I can get my R squared, right? And this is now with 5 trees, right? And here we are. We have a model of Blue Duck for bulldozers with a 71% R squared. With a random forest we wrote entirely from scratch.
Wow.
So that's pretty cool. Any questions about that? And I know there's like quite a lot to get through, so like during the week.
I don't think I have the capacity to ask questions.
feel free to ask on the forum about any bits of code you come across. Can somebody pass the box to Masha? Oh, there it is.
Thank you. The main reason for the ghosts and pumpkins that are here is actually so that I can monitor how bad the face tracking is. Because like I don't always move that much, but the ghosts and pumpkins are always moving. And it was bad at the beginning, but now it's getting better, so yes, they're here to protect us, I guess. And also it's in season. There are like other things that I can choose. There was another one that's a sheep, but I don't want to make us sleepy.
Can we get back to the probably to the top, or maybe
Thank you.
the decision tree when we set the score equal to infinity, right?
Yes.
Do we calculate this score for the? I mean, like I lost track of that, and specifically, I wonder when we implement find var split. We check for self score equal to whether it's equal to infinity or not.
Mm-hmm.
It seems like unclear whether we fall out of this. I mean, like if we ever implement the method, if our initial value is infinity.
Okay, let's talk through the logic. So the decision tree starts out with a score of infinity. So in other words, at this point, when we've created the node, there is no split, so it's infinitely.
And you can start it out with any value you like. It could even, I mean, I wouldn't recommend it, but it can even be a string. It's something that tells you this node doesn't have a score, right? So it can be 0 if you want, it could be -1, but we're just choosing infinity, right? And then when there's a score, you put it there. But we're not putting any other value like 0 or -1, so that if the value itself is 0 or -1, then we don't want to mess with that. And have our initial state be close to our final state. So infinity is like, we're never going to get there, so let's have it be that.
Bad.
Oh,
Okay?
What did you say?
So there is no split, so it's infinitely bad. Okay? So that's why the score is infinity. And then we try to find a variable and a split that is better. And to do that, we loop through each column and say, hey, column, do you have a split which is better than the best one we have so far? And so then we implement that. Let's do the slow way, since it's a bit simpler. Find better split. We do that by looping through each row and finding out, this is the current score, if we split here. Is it better than the current score? The current score is infinitely bad, so yes it is. And so now we set the new score equal to what we just calculated, and we keep track of which variable.
And that's why it has to be it's like as big as it can be so that we can make it smaller. Now I'm actually understanding our last point where I was saying why we're minimizing it. But yes, we're minimizing the RMSC, I guess, or just MSC, because there's no squared.
We chose and the split we split on. Okay, no worries. Okay, great. Let's take a 5-minute break, and I'll see you back here at 22. So when I tried comparing the performance of this against scikit-learn, this is quite a lot slower. And the reason why is that although like a lot of the work's been done by NumPy, which is nicely optimized C code, think about like the very bottom level of a tree. If we've got...
Is the very bottom level of a tree the root or the leaves?
a million data points, then the bottom level of the tree has something like 500,000 decision points with 1 million leaves underneath, right? And so that's like 500,000 split methods being called, each one which contains multiple calls to NumPy, which only have like one item that's actually being calculated on. And so it's like, that's like very inefficient. And it's the kind of thing that Python is particularly not good at performance-wise, right? Like calling lots of functions lots of times. I mean, we can see it's not bad, right? You know, for a kind of a random forest which 15 years ago would have been considered pretty big, this would be considered pretty good performance, right? But nowadays this is some hundreds of times at least slower than it should be. So what the scikit-learn folks did to avoid this problem was that they wrote their implementation in something called Cython. And Cython is a superset of Python. So any Python you've written, pretty much, you can use as Cython, right? But then what happens is Cython runs it in a very different way. Rather than passing it to the kind of the Python interpreter, it instead converts it to C, compiles that, and then runs that C code, right? Which means the first time you run it, it takes a little longer because it has to go through the kind of translation and compilation. But then after that, it can be quite a bit faster. And so I wanted just to quickly show you what that looks like, because you are absolutely going to be in a position where Cython's going to help you with your work. And
performance-wise, so first time is going to take a while, but then later on it will be faster than normal Python because it's running on C.
Most of the people you're working with will have never used it, may not even know it exists, and so this is like a great superpower to have.
Oh, hi. Prague. I mean, thank you.
Load extension Cython, right? And so here's a Python function, fib1. Here is the same as a Cython function. It's exactly the same thing with %% at the top. This actually runs about twice as fast as this, right? Just because it does the compilation. Here is the same version again, where I've used a special Cython extension called cdef, which defines the C data type of the return value and of each variable, right? And so basically that's the trick that you can use to start making things run quickly, right? And at that point, now it knows it's not just some Python object called T. In fact, I probably should put one here as well. Let's try that. So we've got fib2, we'll call that fib3.
We need that for each line?
So for fib3, yeah, so it's exactly the same as before.
What does fib stand for? Is it Fibonacci? No.
But we say what the data type of the thing we passed to it is, and then define the data types of each of the variables. And so then if we call that, okay, we've now got something that's 10 times faster, right? So yeah, it doesn't really take that much extra, and it's just Python with a few little bits of markup. So that's like, it's good to know that that exists, because
10 times faster. Wow.
If there's something custom you're trying to do, it's actually, I find it kind of painful having to go out and, you know, go into C and compile it and link it back and all that, whereas doing it here is pretty easy. Can you pass that just to your right, please, Masha?
So when you're doing like for the Python version of it, so in the case of an array or an MP array, is it a specific C type of?
Yeah. So there's like
object
a
for
lot
that?
of specific stuff for integrating Python with NumPy, and there's a whole page about it. Yeah, so we won't worry about going over it, but you can read that and you can basically see the basic ideas. There's this C import, which basically imports a certain types of Python library into the.
Fibonacci, yes. So what you're using is yeah. Oh, okay. Yes. I just thought that all the Fibonacci I've seen is either written. I think he was just testing it. Was it like a full-on Fibonacci, or was it just for? I know there are like different ways. It's not only recursive to run it, but yeah. Okay. And also, I actually didn't know about Python before, but I think in here, in the description of this lesson, they're discussing it. Otherwise, I actually didn't know about its existence. Oh, they're not? Yeah, no, here. Here they're saying that we'll have a quick look at Python. So I didn't know about its existence. How's the motorcycle sound today? One just passed by, that's why I'm asking.
Kind of the C bit of the code, and you can then use it in your Python. So, yeah, it's pretty straightforward. Oh, good question. Thank you. All right, so your mission now is to implement
Python?
confidence based on tree variance, feature importance, partial dependence, and tree interpreter for that random forest. Removing redundant features doesn't use a random forest at all, so you don't have to worry about that. Extrapolation is not an interpretation technique, so you don't have to worry about that. So it's just the other ones. So confidence based on tree variance, we've already written that code, so I suspect that the exact same code we have in the notebook should continue to work. So you can try and make sure it get that working. Feature importance is with the variable shuffling technique. And once you have that work,
Okay, I tried to make the sound lower, so I hope it worked. Or maybe they're just not in a hurry. It's Friday, you know.
working, partial dependence will just be a couple of lines of code away, because rather than shuffling a column, you're just replacing it with a constant value. Right? But it's nearly the same code. And then tree interpreter is going to require you writing some code and thinking about that. But once you've written tree interpreter, you're very close, if you want to creating the second approach to feature importance, the one where you add up the importance across all of the rows, which means you would then be very close to doing interaction importance. So it turns out that there's actually a very good library for interaction importance for XGBoost, but there doesn't seem to be one for random forest. So you could start by getting it working on our version, and if you want to do interaction importance, and then you could get it working on the original sklearn version, and that would be a cool contribution. Right? Sometimes writing it against your own implementation is kind of nicer because you can see exactly what's going on. Right. So that's your job. You don't have to rewrite the random forest. Feel free to if you want to, practice. So if you get stuck at any point, ask on the forum. Right. There is a whole page here on wiki.fast.ai about how to ask for help. So when you ask your co-workers on Slack for help, when you ask people in a technical community on GitHub or Discourse for help or whatever.
That's actually cool. Etiquette of asking for help, for technical help. Because, like, I feel like some beginners are just like, my code isn't running. That's it. That's the only line they put.
Asking for help the right way will go a long way towards, having people want to help you and be able to help you, right?
Mm-hmm.
So like, search for your answer, like search for the error you're getting, see if somebody's already asked about it. How have you tried to fix it already? What do you think's going wrong? What kind of computer are you on? How is it set up? What are the software versions? Exactly what did you type and exactly what happened, right? Now, you could do that by taking a screenshot. So, make sure you've got some screenshot software that's really easy to use. So if I were to take a screenshot, I just hit a button, select the area, copy to clipboard, go to my forum, paste it in, and there we go, right? That looks a little bit too big, so let's make it a little smaller, right? And so now I've got a screenshot. People can see exactly what happened. Better still, if there's a few lines of code and error messages to look at, create a gist. A gist is a handy little GitHub thing which basically lets you share code. So if I wanted to create a gist of this, I actually have a extension. There we are, that little extension. So if I click on here, give it a name, say make public, right? And that takes my Jupyter notebook, shares it publicly. I can then grab that URL, copy link location, right? And paste it into my forum post, right? And then when people click on it, then they'll immediately see.
Is it the whole code or just
my notebook when it renders?
the whole thing?
Okay, so
then you know how to, because depending on how public you can be, this notebook, still, I feel like people would be worried about students taking their answers, but sharing the whole thing is actually better.
That's a really good way. Now, that particular button is an extension. So on Jupyter, you need to click NV extensions and click on Gist it, right? While you're there, you should also click on collapsible headings. That's this really handy thing I use that lets me collapse things and open them up. If you go to your Jupyter and don't see this NV extensions button, then just Google for Jupyter NV extensions. It'll show you how to pip install it and get it set up, right? But those two extensions are super duper handy. All right. So other than that assignment...
All right. So it actually... random forests are actually over. I feel like we should do something celebratory. Random forests are over. I'm not gonna close the stream, at least not for, I don't know, like 10-15 minutes, but random forests are over. Okay, let me go back. So we're starting. What is S? GD. GD is gradient descent. What does the S stand for? About machine learning. A reminder from lesson 1. Okay, let's go. And we'll be working with MNIST, which means for now it's going to be vision, computer vision.
We're done with random forests, and until the next course, when you look at GBMs, we're done with decision tree ensembles. And so we're going to move on to neural networks, broadly defined. And so neural networks are going to allow us to go beyond just, the kind of nearest neighbors approach of random forests, all the random forests.
Okay. Random forests are different ways of nearest neighbors.
Forest can do is to average data that it's already seen. It can't extrapolate. It can't calculate, right? Linear regression can calculate and can extrapolate, but only in very limited ways. Neural nets give us the best of both worlds. We're going to start by applying them to unstructured data, right? So unstructured data means like pixels or the amplitudes of sound waves or words, data where everything in all the columns are all of the same type,
Yes, until now we've been looking at data that comes from tables, and I think it's more interesting to look at data that is unstructured, qualitative, not data that's... I think all of the Kaggle... Okay, I'm probably wrong. I was like, all of the Kaggle competitions have table data, but not really. Yeah. So, especially when it comes to vision, it's pixels. You could get some metadata, but it's pixels. And yeah, you can turn that into numbers and work with it. But yeah, it's like working with NLP with language and saying that each letter is not useful. So I don't know about pixels, how we're going to deal with them. I don't really have enough information about computer vision. So let's see. I feel like there's a possibility of me just taking the next lesson, but I should be, I shouldn't make promises because I'm like just excited about what we're learning. So why am I pausing it? Let's learn.
As opposed to like a database table where you've got like a revenue and a cost and a zip code and a state. It should be structured data. Okay. We're going to use it for structured data as well, but we're going to do that a little bit later. So unstructured data is a little easier, and it's also the area which more people have been applying deep learning to for longer. If you're doing the deep learning course as well, you'll see that we're going to be approaching kind of the same conclusion from two different directions. So the deep learning course is starting out with big, complicated convolutional neural networks being solved with, sophisticated optimization schemes, and we're going to kind of gradually drill down into like exactly how they work.
So technically I'm still here, but there's an issue with my avatar. Don't worry. I'll try to fix it.
Complicated is of the same conclusion from two different directions. So the deep learning course is starting out with big, complicated convolutional neural networks being solved with, sophisticated optimization schemes, and we're going to kind of gradually drill down into like exactly how they work. Whereas with the machine learning course, we're going to be starting out more with like, how does stochastic gradient descent actually work? What do we do? What can we do with
what? Stochastic?
With the machine learning course, we're going to be starting out more with like, how does stochastic gradient descent
Stochastic? What does that mean?
actually work? What do we do? What can we do with like one single layer, which would allow us to create things like logistic regression? When we add regularization to that, how does that give us things like ridge regression, elastic net, lasso? And then as we add additional layers to that, how does that let us handle more complex problems?
Stochastic means probabilistic. Why? Why are there two words for that?
And so we're only going to be looking at fully connected layers in this machine learning course. And then I think next semester with your net, you're probably going to be looking at some more sophisticated approaches. And so, yeah, so in this machine learning, we're going to be looking much more at like what's actually happening with the matrices and how are they actually calculated. And the deep learning, it's much more like what are the best practices for actually solving, you know, at a world-class level, real-world deep learning problems. Right?
Okay.
So next week, we're going to be looking at like the classic MNIST problem, which is like how do we recognize digits. Now, if you're interested, you can like skip ahead and like try and do this with a random forest, and you'll find it's not bad.
Okay.
Right? Given that a random forest is basically a type of nearest neighbors, right? It's finding like what are the nearest neighbors in tree space. Then a random forest could absolutely recognize that this 9, those pixels, you know, are similar to pixels we've seen in these other ones, and on average they were 9s as well, right? And so like we can absolutely solve these kinds of problems to an extent using random forests. But we end up being rather data limited because every time we put in another decision point, you know, we're halving our data roughly. And so there's just this limitation in the amount of calculation that we can do. Whereas with neural nets, we're going to be able to use lots and lots and lots of parameters using these tricks we're going to learn about with regularization. So we're going to be able to do lots of computation, and there's going to be very little limitation on really what we can actually end up calculating as a result.
Okay.
Great. Good luck with your random forest interpretation, and I will see you next time.
Great. Lovely. So, are we back? Technically, yes. So I just got some information that I need to go somewhere. So I'm not gonna actually continue this lesson, even though, lesson 7 is done. So we will be going to lesson 8, inshallah, next time. So that's gonna be cool. Probably it's going to be gradient descent. And I gotta run. And she's stuck. Great. Lovely. I wish you... Oh, to confuse students, of course. I guess that's why there are 2 words for the same concept. I remember a course in uni called stochastic methods that we had to take after probability and statistics. That seems like a lot of fun, like tons of fun. Just concepts. Alright, I gotta run because someone needs me, and I wish you a lovely weekend. And if it's not the weekend, you'll get there, no worries. Thank you for being here. Today's lesson was, I'd say, a bit short. And sorry for the technical issues. Life happens. We've been here less than an hour. Can you believe that? It's even a weekend. Let's try to do better tomorrow. And I'm saying that for myself. Thank you for your time, for being here. I appreciate it. Thank you. Let's learn awesome things together. Okay. I'm gonna close this out. I think I can go with 5. 4, 3, 2, 1. Thanks for being here. Goodbye.